So let us take the first property. So take the linearity property. So linearity property. So it is quite common for all the transforms which you are going to see. Take the statement. So can anyone start recording? Okay, started, right? It is started, fine. So you can take if x of t Fourier transform is equal to x of j omega and y of t Fourier transform is equal to y of j omega, y of j omega. So then z of t is equal to a into x of t plus b into y of t. The Fourier transform is equal to, so z of j omega. So this is equal to a into x of j omega plus b into y of j omega, b into y of j omega. So this is a property which is called as a linearity property. So right, let us consider the proof of this one. We'll consider the proof of this property. So take the proof. We'll consider the proof. So in order to prove this one, we'll consider the DTFT of the Z of t will consider. Sorry, the Fourier transform of the Z of t will consider. That is the Fourier transform of Z of t, which is nothing but. So already we know this property. It's very simple among all the properties. So it is Z of j omega. So this is equal to integral from minus infinity to plus infinity Z of t into e to the power of minus j omega t into dt. E to the power of minus j omega t into dt. Now, in place of z of t, I'm going to substitute z of t is equal to a into x of t plus b into y of t. I'll substitute. So z of j omega. So this is equal to integral from minus infinity to the plus infinity. So I'm going to substitute as a into x of t plus b into y of t. So into e to the power of minus j omega t into dt. Now let us split the integrals here. So we'll split the integral parts here. So it is very simple. E to the power of minus j omega t into dt plus b into integral from minus infinity to the plus infinity. So y of t into e to the power of minus j omega t into dt. E to the power of minus j omega t into dt. Okay, now this is nothing but the x of omega, and this is nothing but y of j omega. So we'll get z of j omega is equal to a into x of j omega plus b to y of j omega. So this is the linearity property. So which is very simplest one among all the properties. Done. So this is the linearity property. So we'll go for the next one, which is called as the time shift property. So take the property number 2, which is called as the time shift property. So shifting the time domain is equivalent to so multiplying the exponential term in the frequency domain. So this one you're going to call it as a time shift property. So it says like this. So already we have done the same thing in the discrete time Fourier transform. Now we'll do for the continuous time Fourier transform. So you can take if x of t, the Fourier transform is equal to x of j omega, then what you are going to get is y of t is equal to the x of t minus t naught. So if you take the Fourier transform of this one, so this has become x of j omega. The Fourier transform of the x of t is x of j omega, and the corresponding minus t naught. So this minus t naught will become e to the power of minus j t naught into omega. Will get minus j t naught into omega. Minus j t naught into omega. So this is the Fourier transform, and similarly we can write like this also. At the end I will write here. So similarly, if it is plus is there, you also will get plus. So at the end I will write that one after proving this property. So now in order to find out the Fourier transform, in order to prove this property, let us consider the Fourier transform of the signal y of t. So y of j omega, so which is nothing but the Fourier transform of y of t. So this is given by integral from minus infinity to plus infinity. So y of t into e to the power of minus j omega t into dt, e to the power of minus j omega t into dt. So this is the Fourier transform of this signal. Now what shall we do is, in place of y of t, let us substitute x of t minus t naught. So it will become y of j omega is equal to integral from minus infinity to plus infinity x of t minus t naught into e to the power of minus j omega t into dt, e to the power of minus j omega t into dt. So this is the in place of y of t we have substituted. So but here whatever the term should be there should not be any shift here. If any shift is there, we are going to do replace with the some other variable. We are going to do it here because we should want a single time instant we want here. So I'm going to substitute let t minus t naught is equal to something called lambda. I'm going to substitute here some variable called lambda. So I'm going to find out for the t and I'm going to replace the dt with respect to the d lambda. We're going to do replace here. So I can take let t minus t naught is equal to, we'll substitute with the lambda. So we'll substitute let t minus t naught is equal to some variable which is called lambda. I'm going to substitute here. So this implies that I need to find out the value for the t. So t is equal to the lambda plus t. Sorry, t is equal to the lambda plus t naught here. T naught go that side, it will become t naught plus t naught. So let us find out the value for, so dt is equal to d lambda and t naught is a constant here. T naught is, yes, any doubts? So I'm finding the value for the t. So t is equal to lambda plus t naught. So we need to find the value for dt. dt is equal to d lambda. So since t naught is a constant, it is equal to 0 we'll get here when I'm going to differentiate this one. So now we need to find out the limits here. So limits of the integration we need to find out. So since the limit is minus infinity and plus infinity, so anything added to that one will become the same thing only. So let us find out the limit here. When so t is equal to the minus infinity, so lambda will also become equal to the minus infinity. And also when t is equal to the plus infinity, the lambda will also become equal to the plus infinity. So the limits will become infinity only. Now let us find out the expression. So y of j omega is equal to the, let us substitute back, the limits will remain same thing. So it has become x of lambda into e to the power of minus j omega. In place of the t, I'm going to replace with the lambda plus t naught into d lambda. So because we can replace dt with the d lambda, we can do replace here. And now let us split the exponentials by applying the law of indices. So integral from minus infinity to plus infinity x of lambda into e to the power of minus j omega into lambda into d lambda. So since t naught is a constant, it is not a function of lambda. I'll take outside the integral here. Outside the integral, I'll take e to the power of minus j omega t naught. Now this is equal to, this will become equal to, so this is the thing, but so the input is x here, the output will be the corresponding capital X we are going to take here, and remove lambda, so the corresponding term will become j omega. So this is the thing, but the dt Fourier transform of the signal x of t, we can write it as x of j omega, and this the remaining terms is e to the power of minus j omega t naught, e to the power of minus j omega t naught. Okay, so this is what we'll get. This is the Fourier transform. That is, the time shift property will become equal to the multiplying the exponential sequence in the frequency domain. So similarly, we can write the other property, that is x of t plus t naught. If I take the Fourier transform, so it is a t minus t naught here. So for the t plus t naught, if you take the corresponding Fourier transform will be x of j omega into plus j omega t naught will get plus j omega t naught. So that is multiplying the exponential series with the plus t naught will be equal to the multiplying with the positive exponential series. So this property you're going to call it as the time shift property. So already we have seen the same thing in the discrete time Fourier transform. So here also we got the same property. Okay, ನಿಮ್ಮ laptop ತಗೊಂಡಿದ್ದೀನಿ. Done. So right, the reverse of this property you're going to call it as a frequency shift property. Let us do that one. So any doubts in this property? So already we have seen the same properties in the Fourier series, Fourier transform, discrete time Fourier transform, and we are seeing in the Fourier transform also. And next in Z transform also, you're going to see the same thing. So take the next property, which is called as the frequency shift property. So frequency shift property. Frequency shift property. So in the frequency shift property, what it says is the shift in the frequency domain is equivalent to the multiplying the time domain contained with the corresponding exponential series. Okay. Now let us take the statement of this property. If x of t Fourier transform is equal to x of j omega, x of t Fourier transform is equal to x of j omega, then y of t is equal to, so I'm going to multiply the time domain content with the constant which is called as a j e to the power of j beta t. I'm going to multiply with the x of t. So this multiplying exponential sequence in the time domain. So if we take the Fourier transform of y of t is y of j omega, and this one is become x of, so it is j, the Fourier transform of x of t is omega here, and it will become omega minus beta will get here. X of j into omega minus beta will get. So this is the Fourier transform of the signal, e to the power of j beta t into x of t, which is nothing but x of j omega minus beta, right? So let us find the proof of this one. Proof of this property. So in order to prove this one, I'll take the dt of t of the y of Fourier transform of the y of t I'll consider here. And in place of y of t, we are going to substitute this one and we'll prove the property. So let us take the Fourier transform of y of t is nothing but y of j omega. So it is integral from minus infinity to plus infinity y of t into e to the power of minus j omega t into dt. Sorry, small omega t into dt. Small omega t into dt. So if it is small omega, it's a Fourier transform. If it is capital omega, it's a discrete time Fourier transform. In place of y of t, we'll substitute these quantities. So it is y of j omega is equal to integral. In place of y of t, I'm going to substitute x of t into e to the power of j beta t into e to the power of minus j omega t into dt. E to the power of minus j omega t into dt. We'll substitute this one. Now in this one, we can take minus j common here. Minus j and t, let us take that common. So this has become integral from minus infinity to plus infinity x of t into e to the power of minus j. So the remaining quantities. So if I take minus j, the remaining thing is omega minus beta into t into dt. Omega minus beta into t into dt. Okay, so this is beta, omega minus beta into t into dt. Now the input is x here, the corresponding output will become, it's a capital X here, and remove t, remove the exponential term. So the remaining quantity will become j into omega minus beta will get, omega minus beta. So this is the Fourier transform of the signal. The Fourier transform of the signal e to the power of j beta t into x of t. So that will become the shift in the frequency domain will get. Shift in the frequency domain will get. So this is called as the frequency shift property we'll call. Frequency shift property. Okay, so the time shift property and frequency shift properties are, it's a one, if you take the one inverse, other one will get here, and vice versa will get here. So I'll go for the next property, which is called as a scaling property. Okay, so take the property number 4, which is called as a scaling property. Scaling property. So scaling is nothing but in the time domain, we are going to scale the time with the scalar a, we are going to do it here. So already we did the same thing in case of the discrete time Fourier transform. So any doubts in the previous properties? Any doubts?
No, sir.
Okay, fine. So let us take the scaling property. If x of t Fourier transform is equal to x of j omega, x of t Fourier transform is equal to x of j omega, then so I'm going to scale the time with the scalar a. So it has become x of a into t. The corresponding Fourier transform will become, the Fourier transform of y of t is y of j omega, and the Fourier transform of this one is, so it has become 1 divided by magnitude of a into x of j omega divided by a. x of j omega divided by a. So 1 by a, magnitude of a into x of j omega divided by a will get x of j omega divided by a. So this is the time scaling property. So in order to prove this one, I'll consider the DTFT of the Fourier transform of the y of t. I'll consider not DTFT, it's a Fourier transform of y of t. Will consider. So it is y of j omega is equal to integral from minus infinity to the plus infinity y of t into e to the power of minus j omega t into dt. Omega t into dt. So in place of y of t, let us substitute x of a t here. So minus infinity plus infinity x of a into t into e to the power of minus j omega t into dt. Okay. Now here only the single term should be there. It should not be multiple terms. So I'm going to substitute. I'm going to replace a into t with a certain variable called lambda. I'm going to replace here because we should have the single term here. So we'll take let a into t is equal to the lambda. Let a into t is equal to lambda. So this implies that so t is equal to the lambda by a. T is equal to lambda by a. T is equal to lambda by a. And similarly, let us find out the value for dt here. So dt is equal to d lambda divided by a. Dt is equal to d lambda divided by a. Okay. Now limits. Since it is minus infinity plus infinity, the limits does not change here. So there is no need to find out the limits. Whenever it is the upper and lower limit are the plus infinity and minus infinity. So it will become y of j omega is equal to integral from minus infinity plus infinity. So x of in place of a into t, I'm going to substitute with the lambda into e to the power of minus j omega. In place of t, I can substitute with lambda by a. Into in place of dt, I can substitute d lambda divided by a. D lambda divided by a. So a is a constant. I can take outside the integral. So it is 1 by a. The integral from minus infinity to the plus infinity x of lambda into e to the power of minus j omega lambda divided by a. So because lambda is a function of integral, so omega by a is the frequency domain content here. So I'm going to rewrite as omega by a into lambda. I'm going to rewrite. Okay. 1 by a minus infinity plus infinity x of lambda e to the power of minus j omega by a into lambda into d lambda. Now I'm going to convert this into the Fourier transform formula. So it is 1 by a is the constant here. The input for this one is it's similar to the Fourier transform formula. So the input is x here. The corresponding output will be equal to the capital X. And here, so remove e minus and lambda because lambda is the time domain content. We are going to replace the time domain content, remove it here. So the corresponding Fourier transform will become, so it is j into omega divided by a will get here. 1 by a into x of j into omega divided by a will get. So this is a omega by a. So since we'll consider the magnitude of a, it can write as magnitude of a also we can write here, no problem. If a is the value, which you are going to consider only the magnitude, so we can write like this. Y of j omega is equal to 1 by magnitude of a into x of j omega divided by a. So this is what the property. So this is the shift. The scaling in the time domain is equivalent to the multiplying the corresponding term with the scalar 1 by a in the frequency domain content and multiplying the amplitude by 1 by a. So this is called as the time scaling property. This is called as a time scaling property. So right. So similar one we are seeing the Fourier transform, discrete time Fourier transform also we are seeing. So now we'll consider the time differentiation property we'll consider. So in the DTFT, we are consider the differentiation in the frequency domain. Now we'll consider the differentiation in the time domain we'll consider and we'll prove that one. That is the next property. So I'll take property number 5. So it is called as a time differentiation. time differentiation property. So in the time domain, we are going to differentiate that one. So we'll see what we'll get in the frequency domain. Okay, so I'll take if x of t, take the statement of this property. If x of t Fourier transform is equal to x of j omega, then if I'm going to differentiate the time domain content with the dt, the corresponding Fourier transform will become equal to the j omega into x of j omega. J omega into x of j omega will get. So this is similar to the time differentiation for the dt of t. Okay. Now, in order to prove this one, I'll consider this is the statement. So in order to prove this one, I'll consider the Fourier transform of the x of t. I'll consider. So I'll take x of j omega. Sorry, in order to prove this one, I'll consider the inverse DTFT form, inverse Fourier transform formula. I'll consider here. Why? Because because we want the term x of t to be there alone, should be there here. So that's why I'm considering inverse Fourier transform formula. So I can take inverse Fourier transform of x of j omega. So this is equal to x of t. You can consider inverse Fourier transform of x of j omega is equal to x of t. It is 1/2 pi. The integral from minus pi to the plus pi x of j omega into e to the power of minus j omega t into d omega. So with respect to omega, we are going to do integrate in order to get x of t. Now what we'll do is, so since we want the differentiation in the time domain, we'll differentiate this one with respect to the t on both the sides. We'll differentiate here. So differentiating x of t with respect to t on both the sides. X of t with respect to t on both the sides. So we'll get the property here. So you can take. So this is plus j omega t, not minus j omega t. So for the Fourier transform, we have minus j omega t. For the inverse Fourier transform, we have plus omega t. Plus omega t. So right now, differentiate both the sides. Differentiate both the sides with respect to the t. With respect to t, we are going to differentiate on both the sides. So this has become dx of t divided by dt. So this is equal to the 1/2 pi, the integral from minus pi to plus pi, and x of j omega is a constant here. So I'm going to retain like this. The differentiation of e to the power of ax is a into e to the power of ax. So in place of a, we have j into omega. So it is j omega into e to the power of j omega t into d omega. So just I'm going to change the terms. Okay, so x of j omega into e to the power of j omega t into d omega. Okay. So now we have 1/2 pi integral from minus pi to the plus pi. So we have j omega into x of j omega. Okay, so into e to the power of j omega t into d omega, j omega t into d omega. Okay, so we'll consider rewrite again like this. So in order to find out the this one, so I'm going to recall the formula for the inverse Fourier transform formula. I'm going to recall here. So let us have a look into this formula. So what we have is x of t is there on the LHS part. On the RHS part, we have 1/2 pi minus pi to pi x of j omega into e to the power of j omega t into d omega. So here x of j omega is the input for the inverse Fourier transform formula. The corresponding output will be x of t is there. Okay, so this one I have written as inverse Fourier transform of x of j omega. So x of j omega is the input. So we are going to get the output as x of t. So this I have written as inverse Fourier transform of x of j omega. So that is equal to x of t will get x of t. So similarly, compare this one with this one. In place of x of j omega, we have j omega into x of j omega is there. And here also 1/2 pi integral is same. This quantity is also same. 1/2 pi integral is also same. This is also same here. So what we can do is, so this one in terms of like this, I can write as the inverse Fourier transform of j omega. Okay, so j omega into x of j omega. So this is equal to what? Dx of t divided by dt. dx of t divided by dt, or else I can write this one also as the dx of t divided by dt, the corresponding Fourier transform. So I can write the inverse Fourier transform of this one is like this, we can write, or else I can write this one as a dx of t divided by dt, the corresponding Fourier transform is equal to j omega into x of j omega. J omega into x of j omega. That's what the proof here. So we can write as inverse Fourier transform of this is equal to the time domain content, or else the time domain content, the Fourier transform is equal to this frequency domain content. We can write like this. Okay. So that's why I written as inverse Fourier transform of x of j omega. So x of j omega is the input here. So the corresponding output is x of t. So similar way I am matching here. So j omega into x of j omega is there. So this one I can write as the inverse Fourier transform. So the corresponding output will be the dx of t by dt. Or else if I am giving this as the input, the output will be this one. Okay. So this is for the Fourier transform. So this is the property which is called as the time differentiation property you're going to call. So differentiation in the time domain is equivalent to the multiplying the frequency domain content with the j omega. J omega. Okay. Now we'll do the reverse of this one. So what we did in this here is we are differentiated in the time domain content. Now we'll do the reverse, that is called the frequency domain differentiation we'll do here. Frequency differentiation we'll do, and we'll do the differentiation in the frequency domain. Let us see what we'll get in the time domain. So take the property number 6. So which is called as frequency differentiation. So frequency differentiation. Frequency differentiation. So in the frequency domain, we are going to differentiate this one. So I'll take if x of t take the statement if x of t Fourier transform is equal to x of j omega. So then what we'll do is, so in the time domain, you're going to multiply j into t with the x of t. The corresponding Fourier transform will become, so d divided by d omega of x of j omega. X of j omega means if you are going to differentiate the frequency domain content, that is equivalent to the multiplying the time domain content with the j into t. J into t. So we'll do the proof of this one. We'll consider the proof. So in order to prove this one, I'll consider the Fourier transform formula I'm going to consider. So we'll take the Fourier transform of x of t. So this is equal to x of j omega. So this is, we'll rewrite the formula for the Fourier transform. So it is x of t into e to the power of minus j omega t into dt. E to the power of minus j omega t into dt. Okay. Now what we'll do is, so since we want to differentiate in the frequency domain, I'll differentiate both the sides with respect to the omega. I'm going to differentiate here with respect to omega. So I can take differentiate both the sides. Differentiate both the sides with respect to omega. With respect to omega. So that if you're going to differentiate here, it will become dx of j omega divided by d omega. So this is equal to, and the RHS part also we are going to differentiate. So since x of t is not a function of omega, this is nothing but a constant here, and this is e to the power of minus j omega t is there. So the differentiation of this one will become equal to the, so the differentiation of e to the power of ax is, so it is minus a into e to the power of ax will get. So it is a is nothing but minus j and t is the a here. It's a constant. So the differentiation with respect to the omega will become minus j into t into e to the power of minus j omega t into dt. Minus j omega t into dt will get. Okay. Now, okay. Now, so I can rewrite this one as, so dx of j omega, so divided by d omega. So this we can write as minus infinity to the plus infinity. So minus j t into x of t. So I'll group these terms together here into e to the power of minus j omega t into dt. So here minus jt into x of t is the input here. The corresponding Fourier transform is equal to this one. So I can rewrite this one as dx of j omega. Dx of j omega. So divided by d omega. So this is nothing but the Fourier transform of minus j into t into x of t. Minus j into t into x of t. Or else we can rewrite as minus j into t into x of t. If I take the Fourier transform, so this has become equal to d divided by d omega of x of j omega. X of j omega. So this is the Fourier transform. So in the statement, so just you can add minus here. So minus it has been skipped here. So you can add minus in the statement of the Fourier transform. So minus jt into dt into x of t will become equal to the, so minus j into t into x of t. In the frequency domain, it is the differentiation of the x of j omega. The differentiation of the x of j omega. So this property is called as the frequency differentiation property. Okay. Okay, so we'll consider the next property. Any doubts in this one? Any doubts?
No,
Any
sir.
doubts? Okay, fine. So now we'll go for the next property, which is called as the convolution property. So already we have seen the convolution in the time domain is equivalent to the multiplication of the DFT Fourier transforms. So we'll take convolution property we'll consider. So let us take the statement. If x1 of t Fourier transform is equal to x1 of j omega, and similarly if x2 of t Fourier transform x2 of j omega, so then we'll consider y of t. Y of t is nothing but it's a x1 of t convolution with the x2 of t. The corresponding Fourier transform. The corresponding Fourier transform is equal to y of j omega. Y of j omega. So this is equal to x1 of j omega multiplied with the x2 of j omega. X1 of j omega multiplied with the x2 of j omega. So that is y of j omega is equal to x1 of j omega into x2 of j omega. So this is called as the convolution property. So in order to prove this one, we'll consider the Fourier transform of the y of t, which is nothing but the convolution integral we'll consider, and we'll substitute in the formula and we'll do some replacements and we'll get the required proof. So the convolution in the time domain is equivalent to the multiplication of their respective Fourier transforms. So I'll take the Fourier transform of the y of t I'll consider. So consider the proof. So the Fourier transform of y of t is equal to y of j omega. So that is integral from minus infinity to plus infinity. So in place of y of t into e to the power of minus j omega t into dt. So we'll write the formula for the y of t. Sorry, it is y of t, right? So it is nothing but x1 of t convolution with x2 of t into e to the power of minus j omega t into dt. So I'll write the formula for the convolution integral. So this is integral from minus infinity to plus infinity. So integral. So it is x1 of tau into x2 of t minus tau into d tau into e to the power of minus j omega t into dt, e to the power of minus j omega t into dt. So what we have is we have substituted the convolution in place of x1 of t convolution with x2 of t. We have substituted this convolution integral. So already we have seen this one in the module 2 Now what we can do is whenever we are going to do substitute the new integral, we are going to do the replacement of that one. We'll interchange the, so this is a function of tau and this is a function of t here. I'll interchange the order of the integration. Okay. And for this one, x2 of t minus tau into e to the power of minus j omega t into, so dt, we can apply the time shift property we can apply and we'll get the required proof here. So, okay. So we can take interchanging the order of the integration. So usually when you are going to substitute the new integral, we are going to interchanging the order of the integration. Interchanging the order of the integration. So if you're going to interchange, so it will become, so this integration, I'll move it here. So it's a function of tau, and this one, x1 of tau, I'm going to keep it here. I'm going to bring along with this integral. So next, the remaining term, it's a function of t. So it is x2 of t minus tau into e to the power of minus j omega t. Okay, so into dt into d tau, because the d tau is the first integral. So this way I'm writing d tau outside here. So this is the function. Now this is similar to the time shift property what we have seen. So this is equivalent to the x2 of j omega into e to the power of minus j tau into omega will get here, minus j tau into omega. So this is similar to the time shift property. Okay. So already we have seen, if you want to just, I'll recall this time shift property. So what we have seen just before. So in the time shift property, the shift in the time domain is equivalent to this one. So that shift you can replace here. X of t minus t naught is nothing but, so we can write as this x of j omega into e to the power of minus, the corresponding shift will become equal to the exponential term. So similar way, we can write for this one also. So the shift can be written as the corresponding Fourier transform we can rewrite here. So we can take by using time shift property, by using time shift property, So what we can write is, so we can write this one as, so y of j omega integral. So it's a x1 of tau. It is there like that. So the Fourier transform of this one is equal to the x2 of j omega. So it has become equal to the x2 of j omega into e to the power of minus j omega tau into d tau. Omega tau into d tau. So here, this is not a function of tau. I can move outside the integral. So this is x2 of j omega, the remaining quantities. So minus infinity plus infinity. So it is x1 of tau into e to the power of minus j omega tau into d tau. So this is similar to the Fourier transform formula. In terms of tau, it is there. So we can, can be written as x1 of j omega multiply with x2 of j omega. So that's what the convolution in the time domain is equivalent to the multiplication of their respective Fourier transforms. So this is called as the convolution property. This is called as the convolution property of the Fourier transform. So right, so we are left out with some more properties. We'll continue in the next class. So any doubts so far? Any doubts so far?
No, sir.
Okay, fine. It's okay. So thank you, everyone. Anyone can stop recording.